All right, 4G. Today we're doing just a little lesson here on what is called global maximum and minimum. We have talked about this concept before, but we're going to have questions that are asking us about it, so we're going to do one here. So let's read through the text. Australia has many high mountain peaks, each of which is a local or relative maximum, because each is the highest point relative to the other peaks in its immediate locality. Mount Kosciuszko is the highest of these, but it is still not a global or absolute maximum because there are higher peaks in the other continents of the globe. Mount Everest in Asia is the global maximum over the whole world. So we're going to be testing for global maximums or minimum values by examining and comparing the turning points, but we'll also have to examine boundary points. We'll have to be given a certain domain that we're looking in, and we'll have to look at those to see where the maximums might be and consider any discontinuities as well. Max? Sure. So, one question. Example number 1. Find the absolute maximum and minimum of f of x equals 6x minus x squared over the domain between x equals 0 and x equals 6. Oh, there's 2 questions, sorry. We are doing 2. I thought it was only 1. Okay, so to find the absolute maximum, I'm going to have to find the zeros and the turning point. What kind of equation is that one there? It's a parabola. So I can even avoid the whole calculus and differentiation part if I know the curve well enough. So let's just do this by factorising. The f of x equals, I'm going to factorise an x out of that quadratic, and that would give me 6 take away x, close bracket. That means I can read off my zeros or my x-intercepts. They will be at x equals 0 from the first one and 6. Good. Because we know this is a parabola, that then makes it really easy to find the turning point, because the turning point is always right in the middle of those 2 things. So that's the axes of symmetry. And all I have to do is average. I go 0 plus 6 divided by 2, which is obviously going to be equal to x equals 3. Once I know the x value of the turning point, I then sub it into my original equation to find the y value. So that would be y equals 6 times 3 minus 3 squared. So that's 18 take away 9, which equals 9. So because we know this is a parabola, we have found the vertex of the parabola, which would have coordinates 3, 9. So we're going to draw it. We have found an x-intercept at 0 and another x-intercept at 6. And conveniently, that is exactly where I was asked to sketch between 0 and 6. I have found a turning point at 3, which goes up to a maximum value up here at 9. So 3, 9. And my parabola is going to come down, and I'm just going to stop at those values because I only want to go between 0 and 6, according to the domain that I was given. All right, so I have to find the absolute maximum and the absolute minimum in that domain that I've drawn. So the absolute maximum is the absolutely highest point that that graph gets to, which is going to be my turning point. Now, when I say what is the maximum value, it refers to the y value of that graph. What is the highest y value that it's going to get to, which is going to be 9. Good. So absolute maximum is 9. That also does mean that's at when x equals 3, but 9, we're after the y value. The absolute minimum is the smallest value that that graph is going to get to, which is 0. which happens at 2 points when x equals 0 and x equals 6. But anyway, that's all we need. All right, that's done. Obviously, not all curves are going to be nice parabolas. So let's do the second one. Find the global maximum and minimum of the function f of x equals x cubed minus 6x squared plus 9 minus 4 over the domain between 0.5 and 5. So let's use some calculus to do this time. Let's find our gradient or our derivative. Our f dash x will be equal to, differentiating my function, 3 comes down the front, x, and I subtract 1 from the power. The second term, I bring the 2 down, it multiplies with the 6 to give me 12x. The third term, 9x, the 9 will stay, the x will disappear, and so will the constant. Once I have found that derivative, we use that to find where the stationary points are by making it equal to 0. Okay, so I'm now going to say when my f dash x equals 0, I will get 3x squared minus 12x plus 9 equals 0, but I haven't written that down because I'm going to try and save myself a little bit of writing here. There is a common factor in that equation of 3. So let's factorize that out. 3 bracket x squared minus 4x plus 3 equals to 0, just saving myself a line. That makes it much easier to factorize because now that inside is a monic quadratic. So I'm looking for 2 numbers that times to give 3 and add to give minus 4. Yeah. Okay, now that it's nicely factorized, I can read off my solutions. Either x is going to be equal to 1 from the first bracket. The 3 is not going to give me a solution. And x is equal to 3 from the second bracket. Okay, because these are points, I want to find the y values before I go any further. So sub those back into the original equation. If you sub x is equal to 1 back into here, we have 1 minus 6, that's minus 5, plus 9 is 4, minus 4. Did I just get 0? I did. Okay, now sub 3 into the equation. Maybe use your calculator, it's easier than doing it in your head. What do we get? You're going to make me tell you, aren't you? Yeah. Oh. All right, y equals minus 4. So we have 2 turning points. Now, a few lessons ago, we learnt how to find out what type of turning points they are. We have 2 techniques that you can use now. First of all, we learnt about the slope, the table of slopes, and we did that method. And then I said when we learnt about the second derivative, we said we can do that. If we can find the second derivative, we can sub into that. What would you like to do? Yes. Table of slopes or second derivative? Yeah, table of slopes. Table of slopes. Second derivative. Second derivative would be faster. Second derivative. Oh. Okay, the trouble is the second derivative should be faster, and I think it should be easier. But you have to still remember your table of slopes, because if you can't differentiate something twice, you have no option but to use that table of slopes. So you still need to be able to use it. So are we happy with second derivative because it's the easy option? Yes. All right, second derivative will be f double dash of x. Going to this first green line here, I want to differentiate that. Bringing the 2 down, I get 6x take away 12. And what I want to do is I want to sub each of my x values into that. So the first one was when x is equal to 1. If I sub f double dash of 1, I'm going to get 6 times 1 minus 12. That is equal to negative 6. Not the 6th part that's important. The negative is the part that is important. If that is negative, it means that my curve is concave down, which means that that is a maximum turning point. So I'm going to have a maximum at the point 1, 0. Let's do it again when x is equal to 3. F double dash of 3 equals 6 times 3, take away 12. So that's 18 take away 12, which is a positive 6 this time. Because it's positive, it means concave up, which means that that is going to be a minimum at 3, negative 4. So I've found my two stationary points. I know that one's a maximum and one's a minimum, but are they the global maximum and global minimums of that curve? Let's draw our graph with the boundary domain that we've been given here to see if it gets any higher anywhere else or lower. So to draw it, haven't got a lot of room here. So I have a point at 1, 2, 3, 4. Okay, so at 1, 0, that's going to be here. 1, 0. That is my maximum. So you can even kind of do a little part of the curve. You know it's going to have to curve around that way to be a maximum. The second point was 3. Whoops. The second point was 3, negative 4. So I'm going to put that down here. And that's going to be my minimum turning point. There would actually be a point of inflection in there as well. Luckily we weren't asked to find that as well. We could even find our y-intercept if we wanted to, but we're not actually, no, we're not, because we want to sketch it between 0.5 and 5. So the curve is going to join up like that so far. But come back to my domain. I need to know what is happening when x is 0.5 and when x is 5. So you need a calculator for this. I'm not going to write it down because there's not a lot of room there. If you sub 0.5 into that equation, so it's 0.5 cubed minus 6 times 0.5 squared, not a very nice thing to sub in, you'll find that there is a point that I'm going to put about here. That point has the coordinates 0.5 and negative 7/8, which is the answer you should get when you sub that 0.5 in. When you sub x is equal to 5, so here's my 2, 3, 4, 5 way down here. If you sub x is equal to 5 into that equation, you will get y is equal to 16. So it's actually getting really high up here. So 5, 16. My graph's going to come up really steeply up there. And don't put arrows on the end because we're only sketching between 0.5 and 5. So now when we've sketched that in my domain, the maximum is not, the global maximum is not this maximum turning point. The maximum value my graph gets to is the 16. The global minimum though, okay, this one doesn't overtake my turning point. So my global minimum is going to come from here, which will be the negative 4. Okay, so let's just write that down. So we're going to have a global max is 16 and the global minimum is minus 4. And that's it.